Hello, and welcome to our astronomy course. Okay, okay, please. So, today we have lecture number 13, and the topic of this lecture is the Jovian planets, Pluto, and Kuiper. So, very interesting. The outmost planet in our solar system are Jupiter, Saturn, Uranus, and Neptune. They are often called the Jovian planets, meaning they are like Jupiter. In fact, they are each individual with separate personality. And this slide compares the four outer four to each other and the Earth. One striking feature is their size. Jupiter is the largest of the Jovian four, over 11 times the diameter of Earth. Saturn is slightly smaller, and Uranus and Neptune are quite a bit smaller than Jupiter and Saturn, but still 4 times the size of the Earth. Pluto, not pictured in this figure, is smaller than Earth's moon, but was considered a planet from the time of its discovery in 1930, until a decision by the International Astronomical Union, IAU, in 2006, that reclassified Pluto as a dwarf planet. You will learn about Pluto's characteristics and the reasons for IAU decision, namely in this lecture. The other features you will notice immediately when you look at this figure is Saturn's rings. They are bright and beautiful and composed of billions of ice particles. Jupiter, Uranus, and Neptune also have rings, but they are not easily detected from Earth and are not visible in this figure. Nevertheless, as you visit this board, you will be able to compare 4 different sets of planetary rings. The 4 Jovian dwarfs have hydrogen-rich atmospheres filled with clouds. On Jupiter and Saturn, you can see that the clouds form stripes and bands that circle each planet. You will find traces of these same types of features on Uranus and Neptune, but less distinct. Models based on the observations indicate that the atmospheres on the Jovian planets are not very deep. For example, Jupiter's atmosphere makes up only about 1% of its radius. Below their atmosphere, Jupiter and Saturn are mostly liquid, so the old-fashioned term for these planets, gas giants, should probably be changed to liquid giants. Uranus and Neptune are sometimes called ice giants because they contain abundant water in solid form. Only near their centers do the Jovian planets have core of the dense material with the composition of rock and metal. None of the Jovian dwarfs has a definite solid surface on which you could walk. You can't really land your spaceship on the Jovian dwarf, but you might be able to land on one of their moons. All of the Jovian dwarfs have expensive satellite systems. In many cases, the moons interact gravitationally, partially adjusting their orbit and also affecting the planetary ring system. Some of the moons are geologically active now, while others show signs of past activity. Of course, geological activity depends on heat flow from the interior. So you might ponder what could be heating the inside of these small objects. Why do you expect the outer planets to be low density form? This should be a familiar argument. In an earlier lecture, you discovered that the inner planets would not incorporate ice when they formed because, because it was too hot at their location near the sun. But contrast, in the outer solar nebula, water vapor could freeze to form ice particles. The icy particles accumulated rapidly into giant protoplanets with density lower than the rocky terrestrial planets and asteroids. Consequently, the giant planets grew massive enough to pull in even lower density hydrogen and helium gas directly from the nebula by gravitational collapse. The ices and carbs made outer planets low density form. Now you can expand your argument. Why do you expect the outer planets to have high density core? Why is Jupiter so large? You can analyze this question by constructing a logical argument that relates the formation of Jupiter to the solar nebula theory. Jupiter grew so rapidly from icy planet Dimorph in the outer solar nebula that it eventually became large enough to be able to continue growing by gravitation collapse. By the time the solar nebula cleared away and ended planet building, Jupiter had captured large amounts of hydrogen and helium. The terrestrial planets are made from a small fraction of the elements present in the solar nebula. But the Jovian planets incorporated abundant hydrogen and helium and were able to become very massive. Now create a new argument. How is the activity on Io, and Europa path? The rings of Uranus are not easily visible from Earth. The first hint that Uranus has rings came from occultation, the passage of the planet in front of a star, during which the rings momentarily block the star's light, observed by astronomers on board the Kuiper Airborne Observatory in 1977. Most of what astronomers know about these rings comes from the observation by the Voyager 2 spacecraft. Their composition appears to be water ice mixed with methane that has been darkened by exposure to radiation. Study the rings of Uranus and Neptune on special astronomy books and notice three important points. First of all, the rings of Uranus were discovered during occultation when Uranus crossed in front of a star. The second, the rings are dark, contain little dust, and are confined by small moons. And third, particles orbiting in the rings around Uranus and Neptune cannot survive for long periods. So the rings need to be resupplied with material from impact on moons, as is also true for the rings around Jupiter and Saturn. Why are the rings of Uranus so narrow? Unlike the rings of Jupiter and Saturn, the rings of Uranus are quite narrow, like hoops of wire. You would expect collisions among ring particles to gradually spread the rings out into thin sheets. So, something must be confining the narrow ring. In fact, two small moons have been found orbiting just inside and outside the epsilon ring. If a ring particle drifts away from the ring, the corresponding moon's gravity will nudge it back into the ring. So they are called shepherd satellites or shepherd moons. More shepherd moons, too small to have been detected so far, are thought to control the other ring. Thus, the rings of Uranus resemble Saturn's narrow F ring. Now expand your argument. How do moons happen to be in the right place to keep the ring narrow? Out on the edge of the solar system orbits a family of small icy worlds. Pluto was the first to be discovered in 1913, but modern telescopes have found more. You might have learned in school that there are 9 planets in our solar system. But in 2006, the International Astronomical Union voted to remove Pluto from the list of planets and reclassify it as a dwarf planet. Pluto is a very small, icy world. It isn't Jovian and it isn't terrestrial. Its orbit is highly inclined and elliptical enough that Pluto actually comes closer to the Sun than Neptune at times. To understand Pluto's status, you must use comparative planetology to analyze Pluto and then compare it with its neighbors. Pluto is very difficult to observe from Earth. It has only 65% the diameter of Earth's moon. In Earth-based telescopes, it never looks like more than a faint point on light. And even in Hubble Space Telescope images, it shows little detail. Orbiting so far from the Sun, Pluto is cold enough to freeze most compounds. You think of gases and spectroscopic observations have found evidence of nitrogen ice on its surface. Pluto has a thin atmosphere of nitrogen and carbon monoxide with small amounts of methane. Pluto has 3 moons, 2 named Nix and Hydra, are quite small, but Charon is relatively large, with half of Pluto's diameter. Charon orbits Pluto with a period of 6.4 days in an orbit highly inclined to the elliptic. Let's look at this left part of the slide, please. Pluto and Charon are tightly locked to face each other. So Pluto's rotation is also highly inclined. Charon's orbit size and period plus Kepler's third law reveal that the mass of the system is only about 0.002 Earth's mass. very, very small, right? Most of that mass is Pluto, which has about 12 times the mass of Charon. Knowing the diameters and masses of Pluto and Charon allows astronomers to calculate that their densities are both about 2 grams per cubic centimeter. And this indicates that Pluto and Charon must contain about 35% ice and 65% rock. The best photos by the Hubble Space Telescope reveal among almost no surface detail, but know enough about icy moons to guess that Pluto has craters and probably show signs of tidal heating caused by interaction with its large moon Charon. The New Horizons spacecraft will fly past Pluto in July 2015, and the image radioed back to Earth will certainly show that the Pluto is an interesting world. To understand why Pluto is no longer considered a planet, you should recall the Kuiper Belt. Since 1992, astronomers have discovered more than 1,000 icy bodies orbiting beyond Neptune. There may be as many as 100 million objects in the Kuiper Belt, larger than 1 kilometer in diameter. There appears to be icy planetary mounds left over from the outer solar nebula. Some are quite large, and one Eris is 5% larger in diameter than Pluto. 3 other Kuiper Belt objects found so far, Sedna, Quar, pronounced by Qua or Var, and Orcus, are half the size of Pluto or even larger. Some of these objects have moons on their own. In that way, they resemble Pluto and its 3 moons. A bit of comparative planetology shows that Pluto is not related to the Jovian or terrestrial planet. It is obviously a member of new found family of icy worlds that orbit beyond Neptune. These bodies must have formed at about the same time as the 8 classical planets of the solar system. But they did not grow massive enough to clear their orbital zone of remnant planetary mass, and consequently remain embedded among a swarm of other objects in the Kuiper Belt. The IAU's criteria for full planet status are that an object must be large enough that its gravity has pulled it into a spherical shape, and also large enough to dominate and gravitationally clear its orbital region of most or all other objects over a span of billions of years. Eris and Pluto, the largest objects found so far in the Kuiper Belt, and Ceres, the largest object in the asteroid belt, are too small to clear their orbit zones of other objects, and therefore do not meet the standard for the being called planet. On the other hand, all 3 are large enough to be spherical, so they are the prototypes of a new class of objects defined by the IAU as dwarf planets. Now, this section is not about 1950s rock band. It is about the history of the dwarf planet And it will take you back 4.6 billions of years to watch the outer planets form. Over 100 Kuiper belt objects are known that are core with Pluto in a 3/2 resonance with Neptune. That is, they orbit the Sun twice, while Neptune orbits 3 times. And these Kuiper belt objects have been named plutonium. The plutoniums formed in the outer solar nebula. But how did they get caught in resonance with Neptune? You have learned that models of the formation of the planets suggest that Uranus and Neptune may have formed closer to the Sun, and that sometimes later, gravitational interactions among the Jovian planets could have gradually shifted Uranus and Neptune outward. As Neptune migrated outward, its orbital resonance could have swept up small objects, like a strange kind of snowflow. The plutoniums are caught in the 3/2 resonance, and other Kuiper belt objects are caught in the other resonances. The evidence appears to support models that predict the Uranus and Neptune migrated outward. This migration of the outer planets would have dramatically upset the motion of some of these Kuiper belt objects, and some could have been thrown inward where they could interact with the Jovian planets. Some of those objects may have been captured as moons, and astronomers wonder if moons such as Neptune's Triton could have started life as Kuiper belt objects. Other objects may have hid bodies in the inner solar system and caused the later heavy bombardment episode, especially evident on the surface of the Earth's moon. The small frozen bores on the fringes of the solar system may hold clues to the formation of the planets nearly 4.6 billion years ago and the subsequent history of our Earth. What evidence indicates that cataclysmic impacts have occurred in our solar system? To build this argument, you must cite plenty of evidence. The peculiar orbits of Neptune's moon, Triton, and Nereid, the peculiar rotation of Uranus and Pluto's large satellite Charon, all hint that impacts and encounters with large planetesimal's or comet nuclei have been important in the history of these worlds. Furthermore, the existence of planetary rings suggests that impacts have scattered small particles and replenished the ring. Even in the inner solar system, the retrograde rotation of Venus, the high density of Mercury, the smooth northern lowlands of Mars, and the formation of Earth's moon are possible consequences of major impacts when solar system was young. And now, assemble evidence in a new argument. How does the origin of the plutonium give a clue about one possible source of impacting bodies in the solar system? No one has even been farther from Earth than the moon. We humans have sent robotic spacecraft to visit most of the larger worlds in our solar system. And we have found them to be strange and wonderful places. But no human has ever set foot on any of them. We are trapped on Earth. We lack the technology to leave Earth. Getting away from Earth's gravitational field is difficult and calls for very large rockets. America built such rockets in 1960s and early 1970s. They could send astronauts to the moon. But such rockets no longer exist. The best technology today can carry astronauts just a few hundred kilometers above Earth's surface to orbit above the atmosphere. The United States is beginning an ambitious plan to build a new generation of human-piloted rockets meant to carry people back to the moon and eventually to Mars. Does Earth's civilization have the resources to build spacecraft capable of carrying human explorers to other worlds? We'll have to wait and see. In the previous lecture, you discovered another reason we Earthlings are trapped on Earth. We have evolved to fit the environment on Earth. Now on the planet or moon you explored in this lecture would welcome you. Lack of air and extreme heat or cold are obvious problems. But also, Earthlings have evolved to live with Earth's gravity. Astronauts in space for just a few weeks suffer biomedical problems because they are no longer in Earth's gravity. Living in a colony on Mars or the moon might arise similar problems. Just getting to the outer planet would take decades of space travel. Living for years in a colony on one of the Jovian moons under the low gravity and exposed to the planet's radiation belt. All of that may be beyond the capability of the human body. We may be trapped on Earth not because we lack large enough rockets, but because we need Earth's protection. It seems like we need Earth more than it needs us. The human race is changing the world we live on at a startling pace. And some of those changes could make Earth less hospitable to human life. All of your exploring often unearthly worlds serves to remind you of the nutrition beauty of our home planet. The Jovian planets, Jupiter, Saturn, Uranus, and Neptune, are large, massive low-density worlds located in the outer solar system. Jupiter and Saturn are composed mostly of liquid hydrogen. And for this reason, they are sometimes referred to as liquid giants. Uranus and Neptune contain abundant water in solid form and are sometimes called ice giants. All the Jovian planets have large systems of satellites and rings that have had complex histories. Jupiter is observed to have heat flowing out of it, and at high rate, indicating that its interior is very hot. Jupiter has a core of heavy elements surrounded by a deep mantle of the liquid metallic hydrogen, in which the planet's large and strong magnetic field is generated. The magnetosphere around Jupiter traps high-energy particles from the sun to form intense radiation belts. Jupiter's atmosphere contains three layers of clouds formed of hydrogenic molecules, including water and ammonia. Atmospheres of the Jovian planet are marked by the belt zone circulation that produces cloud belts parallel to the equator. Zones are high-pressure regions of rising gas, and belts are lower-pressure areas of sinking gas. Spots in Jupiter's atmosphere, including the Great Red Spot, are circulating weather patterns. The four large Galilean moons show in sign of geologic activity: groove terrain of Ganymede, smooth ice and cracks on Europa, and active volcanoes on Io. Shows that tidal heating driven by orbital resonances has made this moon active. Many of Jupiter's moons are small, rocky bodies that could be captured objects. They are too small to retain heat and are not geologically active. Jupiter's ring is composed of dark particles that are bright when illuminated from behind, which is called forward scattering. This shows that the particles are very small and are probably dust from meteoroid impacts on Moon. Jupiter ring, like all of the rings in the solar system, lies inside the planet's Roche limit, within which tidal stress can destroy a moon or prevent one from forming. Saturn is less dense than water and contains a small core and less metallic hydrogen than Jupiter. Cloud layers of Saturn occur at the same temperature as those on Jupiter. But because Saturn is faster from the Sun and colder, the cloud layers are deeper in the hydrogen atmosphere, below a layer of methane gas, and so are less prominent. Saturn's moons are icy and mostly heavily cratered. Saturn's largest moon, Titan, has a cold, cloudy nitrogen atmosphere. It may have had methane falling as rain on its icy surface and forming lakes and rivers. Sunlight entering Titan's atmosphere can convert methane into the complex carbon-rich molecule to form haze and particles that settle out to coat the surface from dark organic material. Enceladus has a light surface with some uncratered regions. Geysers of water and ice went from the region around its source pole and provide ice particles to the E ring. Saturn's rings are composed of icy particles ranging in the size from boulder to dust. The composition and brightness of the ring particles vary from place to place in the ring. Grooves in the ring can be produced by orbital resonances or waves that propagate through the ring, caused by moons near or within the ring. Narrow rings and sharp rings edges can be produced by shepherd satellites. The material observed now in the Jovian planet rings cannot have lasted since the formation of the solar system. The rings must be replenished occasionally with material produced by meteoroids, asteroids, and comets colliding with Moon. Uranus is much less massive than Jupiter, and its internal pressure cannot produce liquid hydrogen. It has a heavy element core and a mantle of solid or slushy ice and rocky material below a hydrogen-rich atmosphere. Little heat flows out of Uranus, so it cannot be very hot inside. Uranus' atmosphere is almost pitiless at visual wavelength with a pale blue color caused by traces of metal, which absorbs red light. Images at selected wavelengths can be enhanced to show traces of belt zone circulation. Uranus rotates on its side, perhaps because of a major impact during its early history, or because of tidal interactions with other planets when it was young. The larger moons of Uranus are icy and heavily cratered with signs of some of past geological activity, including a void on Miranda. The rings of Uranus, discovered by stellar occultations, are narrow hoops confined by Shepherd satellites. The particles appear to be ice with traces of metal darkened by the radiation belt. Neptune is an ice giant like Uranus with no liquid hydrogen. Unlike Uranus, Neptune does have heat flowing outward from its interior. The atmosphere of Neptune, marked by the traces of belt zone circulation, is rich in hydrogen and colored blue by traces of metal. Neptune's satellite system is odd in that distance Nereid follows an elliptical orbit and Triton orbits backward. These may be signs of catastrophic encounters with other objects early in the solar system's history. Triton is icy with a thin atmosphere and frosty polar cap. Smooth areas suggest past geological activity, and dark smudges mark the location of active nitrogen geysers. Neptune's rings are made of icy particles in narrow hoops and contain arcs produced by the gravitational influence of one or more moons. Pluto is a small icy dwarf with 3 moons, one of which, Charon, is quite large in relation to Pluto. The moon's orbital planet, the plane, and Pluto's equator are highly inclined to Pluto's orbit around the Sun. Pluto, now classified by the IAU as a dwarf planet, is a member of a family of icy bodies in the Kuiper belt, orbiting beyond Neptune. At least one of these objects, Eris, is a bit larger than Pluto. Some Kuiper belt objects, called plutonians, follow orbits like Pluto that have an orbital resonance with Neptune. Model calculations suggest that Uranus and Neptune formed closer to the Sun and migrated out, pushing millions of icy bodies in orbital resonances farther from the Sun to form the Kuiper belt. Pluto may be one of those objects. Next lecture will be interesting too. It's called Meteorites, Asteroids, and Comets. And now, I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.